by using the relationship of how many backscatter. So if we think about the probability of backscattering, which is the exact same thing that we saw Rutherford calculate using the 20 divided by 132,000, but in our case, the probability of backscattering is going to be the number of balls that backscatter, and that's going to be divided by the total number of ping pong balls. So do you remember what that was? 266. Good information retention. All right. So we have the probability here. So in terms of the number of balls scattered over the total, we can also relate the probability to the area of all of those nuclei divided by the total area that the atoms take up. Right, this makes a lot of sense because if the entire atom was made up of nuclei, then we would have a 100% probability of hitting one of these nuclei and having things bounce back. So here we have the area of the nuclei we'll figure out, adding those all together, versus the space of all of the atoms put together. So, not only did Professor Sayer, who's in the chemistry department, who put together this contraption for all of you, not only did she magnify the size of these gold nuclei, but she actually had to smush all of these atoms closer together than they normally would be. If, in fact, a gold nucleus was this size here, we would need to use another lecture hall in order to find a place to put this nucleus right here. This is a little bit of a tricky experiment, so we decided we'll just smush it all in and we'll actually be able to account for it because we'll take into account the area of all of those atoms. Oh, I think this board does not like to go by itself. All right, so we can figure out what that is. The area of all of the nuclei is going to be the number of nuclei times the area per nucleus. And we're going to talk about the cross-section here to keep it simple. And all of that is divided by the area of the atoms, which is 1.39 meters squared, measuring that space there. So the number of nuclei, if we were to sit and count these as well, is 119. So we'll multiply that by just pi r squared to get that cross-section, and divide all of that by 1.39 meters squared. So what we have here is a relationship that can tell us what the probability of backscattering is, but what we want to pull out, since we can experimentally measure what the probability is, what we need to pull out is the radius or the diameter of these nuclei. So we can just, instead of solving for p, we can switch it around and solve for the radius. So that's going to be equal to the probability raised to the 1/2 times 6.098 times 10 to the -2 meters. So actually, just for discussion's sake, it makes a little more sense for us to talk about the diameter. So that's just twice the radius. So once we figure out what our probability of backscattering is, we'll just raise that to the 1/2, and we'll multiply that by 12.20 centimeters. All right, so now all we have to do is figure out this probability of backscattering. We know we need to divide by 266. But what we need you to help us with is to figure out this top number here and see how many particles are going to backscatter. So